Hi, this is Jonathan Gardner. We're covering section 1.1 of Schroeder's An Introduction to Thermal Physics. This covers thermal equilibrium. You can think of this as a lecture, but really this is what I've been studying and what I'm learning, and I'm sharing it with you. If you have any questions or anything, of course, I'm here to answer questions. You can join me in Discord, etc., etc., etc. Anyway, so this is the first section of thermal physics. And he talks about a really important concept, and the concept is called thermal equilibrium. So we're going to talk a little bit about temperature, and with thermometers, we're going to start to define some useful terms that we're going to see throughout the course here. And we're going to develop a really basic understanding of what temperature is, at least enough that we can get started in talking about thermal physics. So the first definition we need to consider is the word temperature. And you probably know temperature already. You know that that's the thing that goes up when it's hot and it goes down when it's cold and stuff like that. So I'm going to give a very naive, simple definition. This is the same definition he gives in the book. And he says it's what you measure with a thermometer. Oh, I had an extra T there. Oh well. It's what you measure with a thermometer. So if you think this is a reasonable definition, it's a very naive definition, right? You stick a thermometer in it that tells you the temperature, that's what temperature is. There's a couple problems with this definition. One of the problems is that the thermometer bit, right? Which thermometer are we talking about, right? If we have different kinds of thermometers that use different materials, how do we calibrate these things together, right? And it also doesn't really talk about what it actually is. It just says that this is how we get the number, right? And so we might call this an operational definition. And we have lots of operational definitions in physics, right? Distance is what you measure with a yardstick, right? Things like that. It tells you, an operational definition tells you how we can measure that quantity. It doesn't give us much information about the actual quantity itself. Now, if you think about how a thermometer works, right? So inside of a thermometer, we have basically a glass tube, and there's a bulb at the bottom. We're talking about a mercury thermometer, and there's like a little slice in that tube, and there's a bulb, and inside there is mercury. And what happens is, as the mercury warms up, it expands, and so you're going to see that mercury rise in that tube, and as it cools down, it contracts, so it'll fall, right? And so there's something happening. Like, why is that mercury expanding? Why is that mercury contracting? There's something more fundamental at play here, that the temperature is actually interacting with, changing that mercury in some way. So what we're really measuring with a thermometer is not temperature directly, but we're measuring the size of that mercury. Okay. Let's try another definition for temperature. This is another definition. Let's see how this one works. So temperature is the thing that is the same for two objects after they've been in contact long enough. So this definition is a little better. One of the reasons why it's better is we don't have to talk about thermometers anymore. And now we have two objects. They have a temperature, so each of them has a temperature. And then the idea is that we bring these into contact somehow, and they exchange temperature or something. But the temperature of these two objects becomes the same after long enough. But there's obviously questions that we should be asking, right? What do we mean by contact? What do we mean by long enough, right? And is there some other quantity that becomes the same as these two objects interact, or is it just temperature, right? So this is a more theoretical definition. And the reason why I'd call it theoretical is because we can use this to form theories, we could talk about it, but really it's not really tied to the actual physical universe. It's more tied to ideas about things, a description of things. So temperature, the question is temperature something that's out there that actually exists, right? And this is more of a philosophical question. Or is it something that we invented because it works? And there might be something else out there, it's just temperature is a really good description of it. And I want you to draw your mind to, there's this theory called caloric theory, right? Let me write about that really quick here. I'm going to call it caloric theory. And the interesting thing about caloric theory is we don't accept caloric theory as accurate and correct, but you can use caloric theory to reason about certain phenomena that happens in thermodynamics, and it will give you the right answer, right? So we don't talk about caloric as a thing, but we do talk about temperature as a thing. And there's really a question like why, like what happened when we stopped seeing caloric in things and we started seeing temperature, okay? So that's a really interesting question. So what is contact? What is long enough? What is something else that might be the same? Okay, so we're going to have thermal equilibrium is a concept. Thermal equilibrium is the state of the two objects after they've been in contact long enough. Okay, so this is the state of the two objects. After they've been in contact. Long enough. Okay, so temperature is the thing that is the same for two objects after they've been in contact long enough, and thermal equilibrium is the state of the two objects after they've been in contact long enough. So after they've been in contact long enough, we say those two objects are in thermal equilibrium, so they have the same temperature. Okay, and we're going to have relaxation time. Okay, relaxation time is how long it takes. To reach thermal equilibrium. Okay, and some textbooks, they are pedantic and they say that relaxation time is like related to some factor of E, which is 2.7. But in Schroeder, he doesn't really have to go that far. He just says that this is long enough, whatever that means for you. Okay. Note that when you have a thermometer and you stick it in something to read its temperature, it takes a while for that thermometer to stabilize, right? So it might rise in temperature, drop in temperature until it kind of starts to slow down, and then it finally reaches the final temperature. And that's when you take a reading. That's the relaxation time. That's how long it takes for the thermometer to reach that stable equilibrium where the temperature isn't changing anymore. Okay? Let's talk a little bit about what contact means. It means that we allow the two objects to exchange energy spontaneously on their own. That's what spontaneously means, on their own. Okay? We call this energy so exchanged heat. So if we have object A over here and object B over there, there is going to be energy flowing from one to the other. We're going to call that energy heat because the temperatures are different. And when that heat stops flowing, it's because those two objects are in thermal equilibrium. Now, we could take these two objects and we could put them together, right? So they're touching. Or we could have, like, for instance, a cup of hot chocolate out in the air. So it's touching the air, right? It's interacting with the air somehow. We could also take two objects and separate them by a pure vacuum, and we'll see that they exchange energy using radiation, okay? And we could come up with different methods to try to prevent any kind of radiation or any kind of thermal exchange between the two objects, but all we've really done is we've increased, sometimes dramatically, the relaxation time. So when we stick an insulator between the two objects, all we've done is says it's going to take a longer time for them to reach thermal equilibrium. The case that is somewhat related to this, but it's different, is consider you had a cup of hot chocolate. So we have a cup of hot chocolate, right? A nice little mug of hot chocolate. And we add into this cream. At first, when you look at the hot chocolate, right? So there's a little steam coming off that thing. You will see that there's like areas where you can say that's definitely cream and areas where you can say that's definitely hot chocolate. But over time, what happens is they mix together, okay? Not only are they exchanging thermal energy so that they come to a thermal equilibrium between the two, but it reaches a point where you can no longer distinguish the two. And so we're going to call that diffusive equilibrium. Diffusive. And what diffuse means is to spread out. So this is an equilibrium that's reached when these two substances spread out and equal each other, okay? And there's another kind of equilibrium, it's called mechanical equilibrium. And for this, I'm going to use the example of a balloon, right? So we went to the store and we bought a rubber balloon, a latex balloon, and we blown air into it, okay? And we notice that as we add more and more air, the balloon increases in size, right? Why doesn't it just expand in size to fill the entire room? Or why doesn't it just maintain the original shape, and as you add more air, it just gets more and more dense? The answer is because it is pushing on the air all around it, and that air is pushing on it, okay? And so the balloon is going to reach a state where it is in equilibrium. We'll call it mechanical equilibrium, okay? And this kind of equilibrium has to do with forces and pushing and volumes and things like that. Okay, so that's mechanical equilibrium. So we have thermal equilibrium, we have diffusive equilibrium, we have mechanical equilibrium, and he draws a nice little table. So he has the equilibrium type, and then he has the exchanged quantity, XCH exchanged. And so he's going to say when there's thermal equilibrium, there was some kind of energy that was exchanged. We call it heat. When there is mechanical equilibrium, then we had the volume of the two objects reach some kind of equilibrium where they don't change anymore. And then when there's diffusive equilibrium, then we're going to see the particles have exchanged until it's become one cohesive mass. Okay. So now we know that when we have two objects in contact with each other, there's actually three kinds of equilibrium we can reach. One of them has to do with temperature. The others have different quantities that we can measure about them. Okay. Let's get a better definition of temperature. So temperature is the measure of the tendency of an object to spontaneously give up energy to its surroundings. And we need a way of telling whether one object has more temperature or less than the other. And the thing that we're going to use is we're going to say when two objects are in thermal contact, the one that tends to spontaneously lose energy is the higher temperature, is at the higher temperature. So this is what we're going to use for the definition of temperature for the time being. In chapter 3, we're going to go more in depth into what temperature actually is. And I can't emphasize enough how important it is to pay attention to what these words mean. So temperature is a measure. So this is a number that we can measure of the tendency of an object to spontaneously give up energy. So an object just sitting, in some environment will spontaneously give up its energy to its surroundings, okay? When you have two objects and there's thermal contact, remember we talked about the different kinds of contact and the different kinds of exchange quantities that might occur to reach the different kinds of equilibrium. The one that tends to spontaneously lose energy is at the higher temperature, okay? So just like we do for potential energy, we imagine there's some slope, and the one that's higher up, the slope, has higher potential energy, right? And so we're going to say the one that loses energy to the other object has the higher temperature. And this will allow us not only to measure what temperature is, but it'll allow us to classify and order all the different temperature measurements we have into a number line, where some numbers are bigger than others, and we can order everything that we can measure the temperature of and to say this is the highest temperature and this is the lowest temperature. Let's talk about what it takes to measure temperatures. So how do we measure temperatures? So we're basically going to try to come up with a thermometer that's actually useful. Most thermometers use thermal expansion. And what thermal expansion is, as the object heats up or cools down, it changes its size, okay? Typically, as the temperature goes up, the size of the object also goes up. But we know that when water cools down, that reaches a point where it actually increases in volume as it cools down. And so water gets bigger right before it freezes. Okay? So we can take a pot of boiling water, right? And we'll have the water here, and it's boiling, right? So we have some kind of heat. That's a fire if you can't tell. And then we have a pot, right? So we have a pot of boiling water. We stick our thermometer in there, and we call this 100 degrees centigrade. Okay? And then we have over here another pot, and we filled this pot full of water and we added ice. Okay, so there's ice water. It's an ice water mixture. Okay? And we've let that stabilize, and we're going to call this 0 degrees Celsius. Okay? And so we have the scale, Celsius scale. And so if we have our thermometer made of mercury, and we mark off down here is where it's 0 degrees Celsius, and up here it's 100 degrees Celsius, then we can mark off here is 50 degrees Celsius, 75, 25. We can mark off a linear scale for the temperature. Okay? What if we used alcohol instead of mercury? So, you know, this shape of thermometer typically has alcohol in it nowadays because mercury is known to be a little bit toxic. Well, the alcohol would expand at different rates, and so maybe what we'll have to do is have a longer thermometer, right? And up here would be 100 degrees Celsius, and down here would be 0 degrees Celsius, and so we'll have a different scale, right, with different intervals, right? And so we can't really say that the distance the mercury or the alcohol has traveled, but we can say what percentage of the way it's gone between 0 and 100, right? What if we used something even that doesn't behave like mercury, or like this? What if we used a strip of metal? So we took like a piece of copper, we've cut it out carefully, and then we've measured it, and we said out here it's at 100 degrees Celsius, and at this distance it's 0 degrees Celsius, and we can do that the same thing for any kind of material that stretches using thermal expansion. Okay. We could also measure the voltage across the barrier of two metals. We can take two metals and sandwich them together and note how the shape flexes and bends as the temperature changes. In the book, he even has a picture of potter's cones, right? Different cones made of a material that will melt at different temperatures. And so there's a number of ways that we can measure temperatures. One of the most interesting ways is we take a bulb of gas and then we measure the pressure, okay? So as the temperature goes up, the pressure will also increase, and as the temperature goes down, the pressure will decrease. And what happens when you play with this device, so let's say we have 0 degrees Celsius here and 100 degrees Celsius here, we'll notice that for different gases, we'll have different lines. Let me grab a little measuring ruler thing here. And so these lines, let me just draw this out really quick here. So we can measure this between those, and then we can project this out to some point there. And then we have another substance, and what it's going to do is it's going to draw a line that points to the same point. And if we had another substance yet, at 0 degrees Celsius, we'll measure that pressure. And then as it increases up to 100 degrees Celsius, it'll go there. And you'll note this also goes to the same point. There's this point here that all of these things tend towards, okay? And this point for gases, we call that absolute zero. And we measure that to be minus 273 degrees centigrade. Okay, so this is the foundation for the Kelvin scale. And if you're not familiar with the Kelvin scale, we have 0 degrees, or we just say 0K is absolute zero. 273K is 0 degrees centigrade. And then that would make 373K 100 degrees centigrade. And somewhere in between there, about 300K is room temperature. Right, so 300K is a temperature that you would survive, okay, if you were put into it. This is neat because now it really doesn't matter what type of thermometer we're using. These, like different gases, will give us the same absolute zero rating. Now, obviously, if we brought the temperature of this gas down, eventually it's going to condense or it'll turn to a solid, and so we can't reach absolute zero, but these lines do point towards absolute zero, okay. We tend to use Kelvin when we do our math for thermodynamics because it has a number of nice properties for the equations that we're going to use. And in the next section, we're going to be using it extensively, and you'll see why we can't use centigrade. Okay, so there are problems in this section, and I'm going to talk about the problems really briefly. these are not hard problems by any stretch of the imagination. Okay, these should be pretty easy. If you have a hard time with these problems, it could be because you're relatively weak in algebra, or you're having a hard time understanding the problem. I don't, go ahead and reach out to me on Discord and let's figure out where you're at. If you need to study something before you go to thermal physics, or if you're just having a hard time understanding the problems. So problem 1.1 should be pretty easy. It's a simple linear equation. Problem 1.2, same thing. Problem 1.3. So problem 1.3 talks about finding the Kelvin, the measure of Kelvin for different temperatures. So human body temperature is 98 degrees Fahrenheit, or about 37 degrees centigrade. The boiling point of water is, of course, 100 degrees centigrade, or 212 degrees Fahrenheit. And the coldest day you can remember, well, that depends on where you live now, doesn't it? Okay. Problem 1.4, does it ever make sense to say that one object is twice as hot? So for problem 1.4, if you're having a hard time thinking about this one, temperature in some sense may mean the ability to heat other objects, right? So like, how many objects can you heat with this temperature? What would it mean to be twice as hot? What should that mean? What do you think it should mean? And then think about what the temperature of the object would be, okay? And then think about how that temperature would be different for centigrade and Kelvin, okay? 1.5, when you're sick with a fever and take your temperature. So nowadays they use these scanners on your forehead that are pretty quick. They take a couple seconds. When I was a kid, we used to use thermometers. I think they had alcohol in them. You'd stick it in your mouth and wait. That took quite a while. And you might have the electronic ones where you press a button, stick it in your mouth, and it'll tell you after a couple seconds. So that's how long they take, right? And you could figure out or choose for yourself whatever you want. If you're having a hard time thinking of number 1.6, number 1.6 talks about why you can't judge temperature by touching things, right? So I'll give you two cases. One of them might be more relevant than the other depending on where you live in the world. So consider it's a very cold, icy day, okay? And you saw a piece of metal and a piece of wood. Which one would feel colder, okay? According to your touch, right? Shouldn't they actually be in the same temperature because they've come to thermal equilibrium with the weather around it, right? Or on the other hand, let's say you live in a hotter climate, you're not used to seeing snow and stuff like that. On a hot sunny day, would you rather walk barefoot on grass, concrete, sand, a wooden deck, or like pieces of metal, right? Now, assuming that they're not in direct sunlight, that they're in the shade, shouldn't they have come into thermal equilibrium with their environment? So shouldn't all of those things have the same temperature? And how would you feel touching those things, right? For number 1.7, I suggest looking up the dimensions of a mercury thermometer online. They come in a pretty standard size and shape. You might have to just look at a picture and estimate how big it is, right? Otherwise, there's not much else to talk about this one. It is a bit of math. Number 1.8 also is you might want to look up on the website or something what the average highs and lows of the region of the world you live in. And the other one for part B is the coiled metal strip, is you might want to notice that the distance, what's the best way to put this? Just think about how the shape would change if the two metals change their length, okay? And number C should be pretty easy and obvious. Okay, if you need more homework help, obviously you can join me on Discord. We can talk about these problems. Please be sure to add a spoiler message so people who are trying to solve these problems on their own don't get spoiled. So anyway, let me know if you need any help. Let me know how this is going. If you have any suggestions or anything like that, of course, I'm open. Guys, have a great day. Take care, and bye-bye.